atomic and nuclear physics. In this video, we take a look at the concept of the hydrogen atom. The hydrogen atom is the simplest atom in nature, consisting of a single negatively charged electron that is moving about or moving around a positively charged proton. You have an electron and a nucleus consisting of a single proton. In Bohr's model, the electron is pulled around the proton in a circular orbit by an attractive Coulomb force. This Coulomb force will lead to the electron potential energy given by U is equal to negative k E squared over R, where k is equal to 1 over 4 pi epsilon naught. So U, potential energy U, is also equal to negative 1 over 4 pi epsilon naught E squared over R. R is the radius of the electron orbit, so the distance of the electron from the proton. E is, of course, the electron charge magnitude, 1.602 times 10 to the negative 19 Coulomb. K is known as the Coulomb's constant, 8.99 times 10 to the 9th power Newton meter squared per Coulomb squared. Epsilon naught is the permittivity constant, is equal to 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. An electron confined to move around the proton, the nucleus, is similar basically in concept to a particle in a box. If we apply Schrödinger's equation to the Bohr's model, it's not surprising that it will result in the energy being quantized, the energy of the electron being quantized. As such, we have the principal quantum number n, where n is equal to 1, 2, 3, 4, 5, and so on. The angular momentum will also be shown to be quantized. We have the angular momentum orbital quantum number, L. Small l is equal to 0, 1, 2, 3, 4, 5, and so on until you have n minus 1. So if n is equal to 4, L will be 0, 1, 2, 3. If n is equal to 10, L is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We also have M, the angular momentum projection quantum number. Small m is equal to negative L plus 1, and so on until 0, and then 1, 2, up to plus L minus 1 and plus L. So if L is 2, M is negative 2, 1, 0, 1, positive 2. The principal quantum number is associated with the total energy of the electron, as we have mentioned. The energy of the electron is quantized, and it is given by the following equation. E sub n is equal to negative E naught over n squared. The particle in the electron, just like particle in a box, the electron rather is limited to these values of the energy. E naught is equal to 13.6 electron volts. So E1, negative 13.6 electron volts over 1 squared. E2 is negative 13.6 electron volts over 2 squared, and so on. E1 is referred to as the ground state of the electron. E2 is the first excited state. E3 is the second excited state. E4 is the third excited state, and so on. On the other hand, the angular momentum orbital quantum number is of course associated with the orbital angular momentum, and which is, as mentioned, quantized. The orbital angular momentum capital L is given by square root of small l times small l plus 1 times h bar. The angular momentum is limited to these values. The angular momentum projection quantum number m is associated with the azimuthal angle and the z component of the angular momentum of the electron. Lz is equal to m h bar is equal to L cosine of theta. So theta is with respect to the z axis because L sub z is the z component of the angular momentum. M pertains to the different possible positions of the angular momentum with respect to the azimuthal angle. Quantum states with different values of the orbital angular momentum are distinguished using spectroscopic notation. When we say quantum states, we're talking about different values of the principal quantum number n. So M1, N2, N3, N4, N5, N6. For each value of n, you have different values of the orbital angular momentum quantum number. So each of these may be distinguished using spectroscopic notation. The designations S, P, D, and F result from historical attempts to classify the atomic spectral lines. N is equal to 1. The only possible L is 0, so you have 1s. N is equal to 2. You have 2. N is equal to 2. And then possible values of L for n is equal to 2 is 0 and 1. So you have 2s and then 2p and so on. S, P, D, and F, G, H, and so on. So that's it for now. In the next video, we'll take a look at the concept of the electron spin and the exclusion principle. So thank you for watching.